Hello my dear students, in the last class we have discussed the various preparations of carboxylic acids. Now we are going to discuss physical and chemical properties of carboxylic acids. First let us discuss about the physical properties of carboxylic acids. So when come to the physical properties of carboxylic acids, lower carboxylic acids are colorless liquids having a pungent odor. So the carboxylic acids which contain 1 to 3 carbon atoms are pungent in nature, they are having pungent odor, and whereas higher carboxylic acids are solids. Okay. Now in this when come to acetic acid, acetic acid is called as a vinegar. Okay, dilute acetic acid. Nearly 5 to 6% of acetic acid is called as what? Vinegar. Vinegar is nothing but 5 to 6% of acetic acid, and more than 90% of acetic acid is called as what? Glacial acetic acid. It means more than 90% pure acetic acid is called as glacial acetic acid. And when come to the solubility of carboxylic acids, you know that lower carboxylic acids means which contain C1 to C4, the carboxylic acids which contain C1 to C4 carbon atoms are soluble in water due to the formation of hydrogen bond. Carboxylic acids can form hydrogen bonds with water. Because of that, these lower carboxylic acids get soluble in water. But when come to, it means as number of carbons in carboxylic acids increases, as number of carbons increases, solubility in water decreases. Why? Because you know that as number of carbons in the carboxylic acid increases, the hydrophobic nature of alkyl part increases. As hydrophobic nature of carbonyl, the hydrophobic nature of alkyl group increases, the solubility gradually decreases. Now due to the presence of hydrogen bond, they can exist, carboxylic acids can exist as dimers, or C double bond O, like this they can exist as dimers due to the formation of hydrogen bonds. Okay, they exist as dimers. And now we will go for a boiling point. When come to the boiling point, the boiling point of carboxylic acids is more than the boiling point of aldehydes, ketones, alcohols having a comparable molecular masses. Okay, if you compare the boiling points of carboxylic acids with the boiling points of aldehydes, ketones, alcohols having comparable nearly same molecular masses, then here it will be more. So the reason is presence of hydrogen bond. Due to presence of hydrogen bonds, the boiling point of carboxylic acids is more than the boiling point of aldehydes and ketones. Whereas in aldehydes and ketones, they are held by DD forces, dipole forces. Okay, dipole forces are weaker than hydrogen bond. So because of this, the boiling point of carboxylic acids is more than the boiling point of aldehydes and ketones. Okay, and next. And here, and one more important point related to solubilities, I said as number of carbons in the carboxylic acid increases, solubility gradually decreases. When come to benzoic acid, this benzoic acid is insoluble in cold water. Okay, insoluble in cold water. That's all. This about the physical properties of carboxylic acids. Next, chemical properties of carboxylic acids. Chemical properties. When come to the chemical properties, it involves various types of bond cleavages. Okay, it involves cleavage of OH bond, and it involves cleavage of COH bond, and involves cleavage of COH group, and involves the reactions in which alkyl group is involved. So like this various types of bond cleavages takes place in the chemical reactions of carboxylic acid. So in that, first we will go for the reactions involving the cleavage of OH bond. So in these reactions we are supposed to remove only hydrogen from the carboxylic acid. Okay. So therefore reactions involving the cleavage of OH bond. Okay. Now here, or else you can say acidic nature of carboxylic acids. Before going to discuss the acidic nature of carboxylic acid, first of all let us compare the acidic nature of carboxylic acids with alcohols, phenols, and carbonic acid. So order of acidic nature is you know, carboxylic acids are more acidic than carbonic acid H2CO3, which is more acidic than phenol. This is very important, you have to remember this order. Carboxylic acids are more acidic than H2CO3, and which is more acidic than phenol, and phenol is more acidic than methyl alcohol, and which is more acidic than water. So therefore basing on this order, what we can say, carboxylic acids are more acidic than carbonic acid, phenols, methyl alcohol, and water. Okay. Now next, so it means carboxylic acids will have a tendency of losing H plus or giving H plus ions. Now RCOOH, this on ionization you will get RC double bond O minus and H plus. So carboxylic acids on ionization will get carboxylate ion. This is called as carboxylate ion, and this is H plus. And here there is an equilibrium. So you can write equilibrium constant called Ka. Ka is equal to concentration of RCOO minus H plus by concentration of RCOOH. And here Ka is called as what? Acid dissociation constant, or else you can also say acid ionization constant. And here, basing on the value of this Ka value, we can say the strength of a carboxylic acid, whether it is a weak acid or strong acid. You know that pKa is equal to minus log Ka, or else you can write pK is equal to log 1 by Ka. So basing on this relation, we can say that as Ka increases, as Ka value increases, pKa value what happens? Decreases. Now, so the strength of the acidic strength of acids, or the strength of acids can be expressed in terms of Ka and pKa. For strong acids, very important, for strong acids Ka is more, and if Ka is more, then pKa will be less, right? So for strong acids, acid dissociation constant is more and pKa is less, whereas for weak acids, okay, here Ka value is less and pKa is more. Okay, in the examination they will ask in terms of K and pK, which is having a more pK value and which is having more Ka value, like that. So this is very, very important. So for strong acids Ka is more and weak acids Ka is less. And you know that if you take a strong acid, generally for a strong acids pKa value will be less than 1. Okay, for strong acids like mineral acids, you know, pKa value will be less than 1. And when if you take a moderately strong acids, for moderately strong acids pKa will be, the value of pKa will be between 1 to 5. Okay, so pK value is nearly from 1 to 5 for moderately weak, strong acids. And for weak acids, the pK value is found to be 5 to 15. 5 to 15. And whereas for extremely weak acids, pKa is greater than 15. For strong acids, pKa is less. So for extremely weak acids, pKa is more than 15. Now we will compare the acidic nature of carboxylic acids with phenols. Just now I said carboxylic acids are more acidic than phenols. Why carboxylic acids are more acidic than phenols? What is the reason? Very simple. Carboxylic acid RCOOH. This on ionization you are getting RC double bond O minus. This is known as carboxylate ion, and we are also getting H plus. Now if you take phenol on ionization, if it loses a hydrogen, here you will get O minus H plus. This is known as phenoxide ion. In these two, carboxylate ion we are getting and phenoxide ion we are getting. Among carboxylate ion and phenoxide ion, whichever is more stable, that forms very easily. So if you compare the stability of carboxylate ion with phenoxide ion, order of stability is carboxylate ion RC double bond O minus. Carboxylate ion is more stable than phenoxide ion. Why carboxylate ion is more stable than phenoxide ion? What is the reason for it? Very simple. Carboxylate ion is having equivalent resonating structures. Due to the presence of equivalent resonating structures, carboxylate ion is more stable than phenoxide ion. When come to the phenoxide ion is having a non-equivalent resonating structures. So let us write the resonating structures of carboxylate ion and as well as phenoxide ion. RC double bond O minus. So its resonating structure is I will get RC O minus and double bond O. So we are getting two equivalent resonating structures. The compound or the species having equivalent resonating structures is more stable than the species having non-equivalent resonating structures. But when come to phenoxide ion, this is phenoxide ion, and I am writing the resonating structures of phenoxide ion. Double bond O minus like this, and this will be involved here and this will be taken by the carbon. You will get double bond O minus. And here when it is involved, this will be taken by the carbon and you will get this is minus double bond O, and finally you will get this one phenoxide ion. And this is having many resonating structures. Phenoxide ion is having many resonating structures. Even though it is having many resonating structures, it is having less stability because all these structures are not equivalent resonating structures. So, but these two are equivalent resonating structures. Because of equivalent resonating structures, carboxylate ion is more stable than phenoxide ion. So, therefore, carboxylate ion will be produced very easily. It means carboxylic acids loses H plus ion very easily than phenols. In carboxylic acids, the species which increase the stability of carboxylate ion will increase the acidic nature, and the species which decrease the stability of carboxylate ion will decrease the acidic nature. For example, say in carboxylic acids RC double bond O minus, this is called carboxylate ion, and the species which stabilizes carboxylate ion will increase the acidic nature, and the species which decreases the stability of carboxylate ion will decrease the acidic nature. It means very important, in carboxylic acids plus I groups, plus I groups like alkyl groups, plus I groups decreases acidic nature, plus I groups decreases acidic nature, whereas minus I groups increase acidic nature. Okay, for example, say I have taken CH3COOH and I have taken CH2Cl COOH. Okay, among this acetic acid and chloroacetic acid, which is more acidic? Chloroacetic acid is more acidic in nature. Why? Because in this chlorine is a minus A group, and whereas in this CH3 is a plus I group. Okay, because of this due to presence of minus I group, this is more acidic than chloroacetic acid is more acidic than acetic acid. And if you take acetic acid and formic acid, CH3COH and HCOOH, in this case methyl group is having it acts as a plus I group, but here there is no plus I group in this. So because of this, formic acid is more acidic than acetic acid. It means the Ka value of acetic acid, formic acid is more than the Ka value of what? Acetic acid. Or else the pK value of acetic acid. Now here I said Ka is more. K is more for formic acid than K of acetic acid. When come to pKa, the pKa of acetic acid is more than the pKa of what? Formic acid. This is very important. We will take one more example. Say I have taken fluorine, COOH, and I have taken Cl, COOH. This is known as trifluoroacetic acid, and this is known as trichloroacetic acid. Among these two, which is more acidic, and why it is acidic? You know that I said minus I groups increase the acidic nature of carboxylic acids. It means as number of minus I groups increase, acidic nature gradually increases. So therefore here you see the minus I effect is more among fluorine and chlorine. Minus I effect is more for fluorine. Because of this, trifluoroacetic acid is more acidic than trichloroacetic acid, and this trifluoroacetic acid is considered as strongest carboxylic acid or strongest organic acid. It is considered as strongest carboxylic acid, trifluoroacetic acid. It is more acidic due to presence of fluorine, 3 fluorine groups, fluorine atoms. They are having minus I effect. Okay. Now the next, here there is an order. It is there in the academy book. So this is a examination point of view. This order is very, very important. You need to remember this order. Okay. Order of acidic nature. So examination point of view, this order is very important. So you have to remember this order. Now the most, just now I said the most acidic carboxylic acid is trifluoroacetic acid, CF3COOH. Next comes trichloroacetic acid. Next comes dichloroacetic acid. Okay, and next comes nitroacetic acid. And the next one is cyanoacetic acid. Okay, and the next one is fluoroacetic acid, then chloroacetic acid, then bromoacetic acid. Okay, next, then formic acid, and 3-chloropropanoic acid, and the next one is benzoic acid. These two are very important. Benzoic acid. Next one is phenylacetic acid, and the next is acetic acid, and the last one is CH3CH2COH, propanoic acid. So this is the order of acidic strength of carboxylic acid, and trifluoroacetic acid is considered as the strongest carboxylic acid. In this among these compounds, this is the weakest. Okay, among these compounds, the weakest acidic carboxylic acid is propanoic acid, and the very, very important is formic acid and the benzoic acid, very important. Okay, among formic acid and benzoic acid, which is more acidic? formic acid is more acidic. So the Ka value of formic acid is more than the Ka of benzoic acid. In terms of pKa, the pKa of formic acid is less than the pKa of what? Benzoic acid. This order is very, very important. Now acidic nature of aromatic carboxylic acid. Say I have taken benzoic acid. Say this is benzoic acid, and here the benzoic acid having electron withdrawing group, and benzoic acid having a electron releasing group. Say this is 2 and this is 3. So all these three compounds are acidic, but the question is which is more acidic and why they are acidic. Okay, you know that I said if a benzene ring is attached with a electron withdrawing group, then okay, that will have a more acidic nature. So therefore order of acidic nature. Among these three, the most acidic is first one. This is second, electron withdrawing group, and the next one is benzoic acid. 1, and next one is 3. Okay, this is the order of acidic nature of benzoic acid. Benzoic acid having a electron withdrawing group and benzoic acid having electron releasing group. We'll take a example for this. Okay, so benzoic acid having electron withdrawing group, that is NO2. NO2 is an electron withdrawing group. Okay, COOH, and it is NO2. Okay, this is more acidic than benzoic acid, and which is more acidic than methoxy. Okay, 4-methoxy benzoic acid. You know, in this NO2 is an electron withdrawing group, and whereas OCH3 it has 2 lone pair of electrons, and it is a electron releasing group. So among these three compounds, okay, para-nitro benzoic acid is more acidic than benzoic acid, and this benzoic acid is more acidic than para-methoxy benzoic acid. This is very, very important. Okay, now next we'll go for the reactions. We are okay, this is about the acidic nature of carboxylic acids. Now we'll discuss the reactions of carboxylic acids involving cleavage of OH bond. Okay, first one is reaction with, or else we'll discuss like this. Say carboxylic acid or COOH. This carboxylic acid react with active metals. When they react with active metals, you know that acids react with active metals and liberate hydrogen gas. So carboxylic acids on reaction with active metals like sodium or potassium or calcium, like that, you'll get say I have taken a sodium metal. When carboxylic acid react with a sodium, you will get a sodium salt of carboxylic acid and liberate hydrogen gas. And if you take potassium, in this case you will get potassium salt of carboxylic acid and hydrogen gas. Now say I have taken sodium hydroxide, or else you can take KOH, or else you can take calcium hydroxide, like this base. You know that acids react with the bases and forms salts. Suppose say I have taken sodium hydroxide. When sodium hydroxide react with the carboxylic acids, you will get sodium carboxylate and water. Okay, and the next one is reaction with the sodium hydride NaH. When carboxylic acids react with the sodium hydride, in this case also you will get a sodium salt of carboxylic acid and hydrogen gas will be liberated. Okay, and next reaction with ammonia. You know that ammonia is a base. When base react with acid, you will get a salt. So you will get RCOONH4, ammonium salt of carboxylic acid, okay, plus H2O. Okay, next very, very important is sodium bicarbonate. You know, carboxylic acids react with carbonates and bicarbonates and liberate carbon dioxide gas. Here you will get RCOONA plus CO2 plus H2O, and this is used, you know, sodium bicarbonate is used for the identification of carboxylic acids. Carboxylic acids react with sodium bicarbonate and liberate carbon dioxide. Brisk effervescence will be produced. So this is the test for sodium bicarbonate test. It is used for the identification of carboxylic acids. And carboxylic acids can also react with disabled bicarbonates and carbonate Na2CO3. Here also you get RCOO Na plus CO2 plus H2O. Is it clear? So these reactions indicate, all these reactions indicate the acidic nature of carboxylic acids, and in these reactions just we are removing a hydrogen from the carboxylic acid. So therefore these are the reactions which involves the cleavage of OH bond of carboxylic acid. Now we will go for the reactions of carboxylic acids which involve the cleavage of COH bond. So second type of reactions involving cleavage of COH bond. So in these reactions we have to remove OH group from carboxylic acid. Okay. So in that the first one is reaction with PCl3, PCl5, SOCl2. SOCl2 is called as thionyl chloride. Okay. When carboxylic acids react with C double bond O, OH, when they react with PCl3, phosphorus trichloride, in this case just now I said from carboxylic acids you have to remove OH group. Okay. You remove this OH by chlorine. You get R, C double bond O, Cl. And you are supposed to take 3 moles of carboxylic acid. You get 3 moles of acid chloride plus H3PO3. Okay, and this is nothing but acid chloride. Okay, and H3PO3 is called as what? Orthophosphorus acid, and its structure is P double bond O, OH, OH and H. Okay, and it is a dibasic acid because we can remove only 2 hydrogens. Okay, H3PO3 is a dibasic acid, whereas H3PO4 is a tribasic acid. Its structure is P double bond O, OH, OH, OH. Here we can remove 3 hydrogens. So it has 3 ionizable hydrogens. So the basicity of H3PO4, this is what? Orthophosphoric acid, whereas H3PO3 is phosphorus acid, and its basicity is 2, whereas here the basicity is 3. Very important. So therefore whenever carboxylic acids react with PCl3 or PCl5 or SOCl2, we will get acid chlorides. We will take one example for this. CH3 C double bond O, OH, acetic acid 3 moles. On reaction with PCl3, here you will get CH3 C double bond O, Cl, acetyl chloride and H3PO3. Similarly, we will take a PCl5, reaction with PCl5, R C double bond O, OH, carboxylic acids, react with PCl5, and here you will get R C double bond O, Cl plus POCl3 plus HCl you will get here. You will get plus HCl. And here we are getting HCl, hydrochloric acid, and the basicity of this hydrochloric acid is 1, because this on ionization you will get 1H plus. Okay, here the basicity of H3PO3 is 2, whereas the basicity of HCl is 1. So when carboxylic acids react with PCl5, in this reaction we will get acid chloride and HCl, whose basicity is 1. Okay. Now here also we can say take the same example, acetic acid. When react with PCl5, we will get plus POCl3 plus HCl. Okay. Now next reaction with SOCl2, thionyl chloride, R C double bond O, OH. When react with SOCl2 in the presence of pyridine, Okay, you will get R C double bond O Cl plus SO2 plus HCl, and these two are what? Volatile products. Okay, and the role of pyridine in this reaction is to remove HCl. Pyridine is a base, okay, and HCl is an acid. So it is used to remove HCl from the reaction mixture. Here also we can take the same example, CH3 C double bond O acetic acid. Whenever acetic acid reacts with SOCl2 in the presence of pyridine, here we will get CH3 C double bond O Cl plus SO2 plus HCl. Next one is formation of anhydrides. Formation of anhydrides. You know that anhydrides we can represent as R C double bond O C double bond O R, right? Symmetrical anhydrides may be symmetrical or unsymmetrical. Okay. Now, so carboxylic acids R C double bond O OH 2 moles. When carboxylic acids are heated with H2SO4 or P2O5, okay, they loses water minus H2O, and you will get R C double bond O C double bond O R. These are called as anhydrides, acid anhydrides, or else here you can write water, and this reaction is called a dehydration. Okay, the dehydration of carboxylic acid gives anhydrides. For example, say I have taken CH3 C double bond O OH, and I have taken one more 2 moles of carboxylic acid is involved, so C double bond O OH, right? When the acetic acid is heated with concentrated sulfuric acid or else P2O5, in this case loss of water takes place. So you have to remove OH from one carboxylic acid and hydrogen from other carboxylic acid. So therefore you will get CH3 C double bond O C double bond O CH3, known as acetic anhydride. Okay, acetic anhydride, or else its IUPAC name is ethanoic anhydride plus water. Okay, clear. So in this you see this reaction is involving cleavage of COH bond and as well as OH bond. Very, very important. This reaction is involving cleavage of COH bond and as well as OH bond. Now next one is C, formation of esters, esterification, or you can write formation of esters. Okay. Now carboxylic acids react with alcohols in the presence of acid H plus, you will get R C double bond O OR plus water. This process, you know, the process of formation of ester from carboxylic acids and alcohols in the presence of acid is called as esterification or else Fischer esterification. Okay. Now, when come to the mechanism of this esterification, in this case, first R C double bond O OH, this is very important. Okay. When H plus interact with this carboxylic acid, and here you know oxygen is having 2 lone pair of electrons, so okay, it will be attracted by the oxygen having 2 lone pairs, and so that you will get R double bond O H plus OH. And in the presence of alcohol, you know, in this case alcohol act as a nucleophile. When these pi electrons are taken by oxygen, then here positive charge will be developed on the carbon, so it attract the alcohol molecule, and you will get R C OH, okay, OH, and it will be OH R, and this oxygen gets a positive charge. Okay. Next, here after this this hydrogen will be released. Okay, when this electron pair is taken by the oxygen, and this H plus will attack on this oxygen, and here you will get R C OH OH, H and you get plus, and this is what OR. Okay, this is the alkyl group which is obtained from a alcohol. And here you know that it is a easily leaving group, it leaves. Okay, when it is involved like this, okay, then it takes up and leaves. You will get R C double bond O H plus, okay, and here it is OR dash. And here this electron pair will be taken by the oxygen and leaves hydrogen. So finally you will get R C double bond O OR. This is the mechanism of esterification. Okay, esterification is nothing but the process of formation of ester from a carboxylic acid and alcohol in the presence of acid. Okay. Next, reaction with ammonia, or else you can write formation of amides. Formation of amides. When carboxylic acids RC double bond OH react with ammonia, you know that carboxylic acids react with base and forms a salt. You will get RC double bond O NH4. Okay, plus. Okay, you will get minus and this is plus. You will get salt, and this on further heating, when this ammonium salt of carboxylic acid, okay, ammonium salt of carboxylic acid is heated, here you will get RC double bond O NH2 known as amides. Okay, known as amides. Here it loses water. So therefore amides it can be prepared from carboxylic acid, or else you can say when carboxylic acids react with ammonia, the final products will be amides. We will take acetamide as an example. CH3 C double bond O OH. When acetic acid react with NH3, you will get CH3 COO NH4. Okay, this is called as ammonium acetate, which on heating produces CH3 C double bond O NH2 plus H2O. It is known as acetamide. Acetamide, or else, okay, this is a common name, and IUPAC name is ethanamide. Ethanamide is the IUPAC name, acetamide is the common name. Okay, so formation, this is the formation of amides from carboxylic acids. And very important is when benzoic acid react with ammonia, here you will get ammonium benzoate, C double bond O NH4 minus, and this is plus, right. This ammonium benzoate on further heating, when it is heated, it gives C double bond O NH2 plus H2O. This is known as benzamide. Okay, benzamide can be prepared from benzoic acid using ammonia. Okay, in this reaction we are getting amides. Okay, so if you want to prepare amides, okay, then carboxylic acid should be allowed to react with ammonia. Next, we will take phthalic acid. This is very important in examination point of view, very important. Say I have taken phthalic acid. This phthalic acid on reaction with ammonia, you will get salt. Okay, when it is heated, it loses water molecules, and you will get C double bond O NH2, C double bond O NH2. This is called as phthalamide. Okay, this phthalamide on further heating, when it is heated, it loses ammonia, and you will get C double bond O NH. This is called as what? Phthalimide. This is very important. Here it is phthalamide, and this is phthalimide. Next, this about the formation of amides, okay, from carboxylic acids. Now we will go for the reactions, third type of reactions. Reactions involving third type of reactions. In that, the first one is partial reduction. Carboxylic acids on partial reduction using this on partial reduction using lithium aluminum hydride or B2S6 diborane, you will get alcohols. You get primary alcohols. Okay, carboxylic acids on partial reduction in the presence of lithium aluminum hydride or diborane produces or give primary alcohols. We will take acetic acid. Acetic acid on reduction in the presence of these reducing agent, you will get CH3 CH2OH. Or else if you take cyclobutane carboxylic acid, this on reduction you will get CH2OH. Okay, in this reduction COH group is converted into CH2OH. Carboxylic acid group will be converted into primary alcohols. And here this B2S6 diborane is not used for the reduction of esters, nitro compounds, halides. Okay, in this case for the reduction of esters, nitro compounds and alkyl halides, B2S6 is not used as a reducing agent. And one more important reduction is carboxylic acids do not undergo reduction with sodium borohydrate. They do not undergo reduction with sodium borohydrate. For example, C double bond O, CH3 I have taken esters, and here I have taken COH. Okay, let us consider this on reaction B2S6 here. Okay, very important. In this ester group is there and carboxylic acid group is there. Among ester and carboxylic acid, which can undergo reduction with B2S6, which can undergo reduction with B2S6? Carboxylic acid. So therefore, in this compound undergo reduction with B2S6, COOH will be converted into CH2OH, but there is no reduction of this ester group. Very important. Okay, now complete reduction of carboxylic acids. B. Complete reduction. Okay, carboxylic acids on complete reduction are COOH on complete reduction in the presence of Hi plus P, strong reducing agent, you will get RCH3, you will get alkanes. Now we will go for the other named reactions like coal-based electrolysis, decarboxylation. First decarboxylation. This you learnt in the alkanes chapter. So sodium salt of carboxylic acids RCOOH when react with sodium hydroxide or active metals like sodium, you will get RCOONA, sodium salt of carboxylic acid. The sodium salt of carboxylic acid on heating with mixture of NaOH and CaO, this mixture is called as what? Soda lime. So sodium salt of carboxylic acid on heating with soda lime, here you will get RH plus Na2CO3. Here you will get alkane having one carbon atom less than the corresponding carboxylic acid. Say I have taken CH3COONA, sodium acetate. Sodium acetate on reaction with on heating with mixture of NaOH and CaO called as soda lime. Now in this case you have to remove like this, and here the leftover is hydrogen that you are supposed to add to the CH3. So you will get CH4 plus Na2CO3. Okay, this reaction is called as decarboxylation. And similarly, if you take sodium benzoate on heating with soda lime, you will get a benzene plus Na2CO3. Okay. Now next one is coal-based electrolysis. You know that sodium or potassium salts of carboxylic acids on electrolysis produces alkanes. So here I am taking 2RCOONA. This on electrolysis 2 moles of H2O. Okay, you get RR plus 2 CO2 plus 2 NaOH and hydrogen. So in this the alkane and carbon dioxide, these two are produced at anode, and whereas hydrogen and NaOH are produced at cathode. And the nature of this mixture after the electrolysis is basic. Due to presence of NaOH, the nature is basic and pH is greater than 7. Okay. Now, or else if this reaction we can write like this also, RCOO Na plus HOH. Now, you break like this, you will get R plus remove CO2, 2 moles of CO2, 2 CO2 plus NaOH, 2 NaOH, and the leftover is hydrogen, right? Like this also you can write. Okay, and this reaction is, in this reaction we can prepare alkanes from sodium or potassium salts of carboxylic acid. This reaction is known as coal-based electrolysis. Now we will go for the reactions which involves alkyl group of carboxylic acid. Reactions, fourth type, involving alkyl group. Here very important reaction is there, that is 𝗳𝗦𝗔 reaction. 𝗳𝗦𝗔 reaction. This is very important. 𝗳𝗦𝗔 reaction known as 𝗳𝗏-𝗏𝗏-𝗧 reaction. Okay, in this when carboxylic acid, this reaction is given only by the carboxylic acids which contain at least one alpha hydrogen. Say this is the carboxylic acid having 2 alpha hydrogens. 2 alpha hydrogens are there. When it is allowed to react with halogen in the presence of red phosphorus, here these hydrogens, alpha hydrogens, will be replaced by halogens. So you will get RCHX and this is COOH. And this on further reaction with halogen in the presence of red phosphorus, again you will get RCX and it is COOH. And this reaction is called as what? 𝗳𝗦𝗔 reaction. Now we will take acetic acid, CH3COH. When acetic acid react with chlorine in the presence of red phosphorus, here halogen may be chlorine or bromine. You can take either chlorine or bromine. Acetic acid on reaction with chlorine in the presence of red phosphorus, here just replace one hydrogen by chlorine. So you will get CH2Cl-COOH, chloroacetic acid plus HCl. Okay, this chloroacetic acid again react with chlorine in the presence of red phosphorus and gives dichloroacetic acid, which on further reaction gives trichloroacetic acid. Or else you can write like this also, CH3COOH. When react with 3 moles of chlorine in the presence of red phosphorus, you will get CCl3COOH plus 3HCl, trichloroacetic acid. If chlorine is taken in excess, the product will be trichloroacetic acid, and if you take 1 mole of chlorine, the product will be chloroacetic acid. And this reaction is known as 𝗳𝗦𝗔 reaction, 𝗳𝗏-𝗏𝗏-𝗧 reaction. This is very important. And this reaction is not given by benzoic acid, because here benzoic acid has no alpha hydrogen, no alpha hydrogens. Okay, and this is also not given by, this is also not given by 2,2-dimethyl propanoic acid, because it has no alpha hydrogen. Okay, so 𝗳𝗦𝗔 reaction is given by the carboxylic acids which contain at least one alpha hydrogen. Now we will go for electrophilic substitution reactions. Electrophilic substitution reactions of benzoic acid. Electrophilic substitution reactions of benzoic acid. Benzoic acid can undergo electrophilic substitution reactions due to presence of benzene ring. You know that aromatic compounds undergo electrophilic substitution reactions. Now, in benzoic acid, this COOH, the COOH group is a ring deactivating. It is a ring deactivating group. It means it decreases the electron density in the benzene ring, and it decreases reactivity towards electrophilic substitution reactions. Okay. So, in benzoic acid, this COH group is a ring deactivating group. It deactivates the ring by decreasing the electron density. Okay. And this COH is a meta directing group. It means when benzoic acid is allowed to take or get one more electrophile on the benzene ring, it will decide the position for the incoming electrophile, and it will decide the meta position for incoming electrophile. So, that is why it is called as meta directing group. How it direct the incoming electrophile to meta position? Why it direct? So, you know, benzoic acid deactivates the benzene ring by -m effect. Here you know that oxygen is more electronegative than carbon. When electrons are taken with oxygen, and these electrons will be shifted like this, and here you will get a positive charge, and this will be involved here, and you will get a positive charge, and when the electrons are involved, you will get positive charge. It means in the resonating structures of benzoic acid, we are getting positive charge at ortho, para positions. There is no electron density at ortho and para position. It means electron density is present at meta positions. It means when it is allowed to get an electrophile on the benzene ring, it will direct the incoming electrophile to the meta position, because at meta position only electron density is more when compared to ortho and para positions. Now, when come to electrophilic substitution reactions of benzoic acid, it can undergo halogenation, nitration, sulfonation. So, benzoic acid on heating with mixture of HNO3 and H2SO4, and I say that COH is a meta directing functional group. So, it directs the incoming electrophile to the meta position, and you will get meta nitro benzoic acid. Okay, meta nitro benzoic acid, and the electrophile involved in this reaction is NO2 plus. The electrophile involved in this reaction is NO2 plus, and when this benzoic acid react with sulfuric acid, here you will get COH and SO3H. Okay. Now, and its name is 3-carboxy-benzene sulfonic acid. Okay. Now, and here the electrophile involved is SO3. Neutral electrophile is involved in this, and benzoic acid on halogenation, when it reacts with chlorine in the presence of Lewis acid such as AlCl3 or FeCl3, they act as what? Lewis acids. Okay. Benzoic acid on reacts with chlorine in the presence of Lewis acids such as AlCl3 or FeCl3, here you will get COH, and we will get chlorine at meta position, and the electrophile involved in this reaction is Cl plus. Okay. And very important is benzoic acid do not undergo Friedel-Crafts. It do not undergo Friedel-Crafts reactions like Friedel-Crafts alkylation and Friedel-Crafts acylation. Why? Because in Friedel-Crafts alkylation or acylation, we are using Lewis acids, and these Lewis acids will react with carboxylic acid group, COH group, and do not allow the formation of electrophiles. So, therefore, this is very important. Benzoic acid do not undergo Friedel-Crafts alkylation and as well as acylation. So, that's all. This about the chemical properties of carboxylic acids.